Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exam. Still on the business of Waec 2024. This time around, we'll be looking at physics practical, talking about students writing alternative B. Maybe for one reason or the other, they were not able to participate in alternative A of physics practical. So what exactly should the question look like? Talking about mechanics, the question should exactly be centered around what we call simple harmonic motion or periodic motion, or what we call oscillatory motion. As you can see in the question displaying on your screen, some of the things you're going to be provided with about two retort stands. You're going to be provided with a thread. You're going to be provided with about 2 meter rules. You're going to be provided with a stop watch and some other materials as deemed necessary. So as you can see in the question on your screen, it says you are provided with two retort stands, 2 meter rules, pieces of thread, and other necessary apparatus. Now, since this is dealing with a periodic motion, this practical is about periodic motion, or what we call simple harmonic motion. Now, the setup is going to be such that you're going to have thread. Let this extrapolated or broken line represent your thread, as you can as well see in the diagram on your screen. You can see you have your retort stand, and then the using your thread, you're going to have to hang your meter rule such that it is about 10 centimeter from the 0 centimeter end, and about 10 centimeter from the 100 centimeter, so that you have 10 centimeter at both the right and the left end of the meter rule. The thread, of course, is going to be clipped to a rigid support. This time around, we'll be using a clamp, and then the meter rule here is going to be set into motion. It's going to be sent into swinging so that it exhibits simple harmonic motion, where the motion is always accelerated, meaning that it is always changing direction, and it is always directed towards the center, the fixed point, which is always proportional to the displacement from the fixed point. Looking at what the question should look like, you can see instruction. The first instruction says set up the apparatus as illustrated above, ensuring that the strings are permanently 10 centimeter from either end of the meter rule. So when we say permanently, so when we say 10 centimeter permanently from the end of the meter rule, it means this should be 10 centimeter, and this should also be 10 centimeter from both ends. Measure and record the length L equals to 80 centimeter. What this is saying is that the length from the thread, that's the thread tied to the retort stand, the length to the meter rule, you should start first making sure that your L is 80 centimeter. You can see that on the second instruction. Hold both ends of the rule and the 80 centimeter. Now, in the next instruction, we were told to hold both end of the meter rule. You are to hold both end of the meter rule, and when you hold both end of the meter rule, you then displace it, like you set it into periodic motion. You make sure that you're not, displacing it through very large angle. Just a small angle, say about 30-degree, is okay. It's just something you can actually gauge by yourself. So you set the meter rule into motion. So let's say this here is my meter rule. It's been hung 10 centimeter from this end, 10 centimeter from this end. Then I'm going to displace it through small angle, then set it into motion so that it exhibits periodic, or what we call simple harmonic motion. In the case of simple harmonic motion, it is always accelerated and the motion is always directed towards the center. The motion here is going to be directly proportional to the displacement from the fixed point. After displacing, we are then told to release so that it oscillates about the vertical axis through its center. Now, for instruction 4, it says determine and record the time t for 10 complete oscillation. So from our stopwatch now, we are going to, when they say 10 complete oscillation here, we have to determine the time it takes to complete 10 oscillations. Remember that for the first instruction, we were told to keep our L at 80 centimeter. After that, we then hold, from the end, displace through an angle and set into oscillation so that it completes 10 oscillation. Now, 10 oscillation here means 10 oscillation here means 10 to and fro movement like this. To and fro movement 10 times. Like if I'm displacing to, fro, 1, to, fro, 2, to and fro, 3, to and fro, 4, to and fro, 5, to and fro, 6, until I get to 10. Of course, you know that there is what we call damped oscillation. Eventually gets to a point where the motion of the meter rule is going to die down, that it's going to be dampened, and then it's going to return back to its main position, or what we call equilibrium position. But before then, we have to determine the time for 10 to and fro movement. The timing for the 10 to and fro movement is represented by small letter t. And for periodic motion, we talk about time for one cycle. The time for one cycle is what we call period, usually represented as capital letter T. Our period is this. If, for example, let's say 10 oscillation here is going to take about 8 seconds, then the timing what this means is that for 10 oscillation, 10 to and fro movement, it is taking 8 seconds. Then the timing it will take to complete just one oscillation, not 10 oscillation now, is what we call the period. And the period is usually given as the time, the old time, okay, which is about 8 seconds, divided by the number of oscillations. So if it will take 8 seconds, just saying for example, for 10 oscillations to be completed, for 10 to and fro movements to be completed, then it means that the time it will take for just one oscillation, one to and fro movement, is going to be the total time divided into 10 oscillation, divided into 10 places. In this case, that will be 8 over 10, and that is going to mean 0.8 seconds. So you see that the total time taken for like 10 oscillation is usually greater than your period. That's the time it will take just for one oscillation. So looking at the question, we were told to, if you look at instruction 8, we were told to tabulate our readings. Talking about the tabulation, okay, we are looking at when the length is 80 centimeter, when the length is 70 centimeter, when the length is 60 centimeter, 50 centimeter, and 40 centimeter. So this is it. We're looking at about 5 repeated readings. So we say serial number 1, 2, 3, 4, 5. When the length from the rate of stand to the meter rule, when the length is 80 centimeter, okay, and we swing or oscillate or set in motion the meter rule, the timing it took was about 18 seconds. And when the length was reduced to 70, that's the length of the thread was reduced to 70, the timing had reduced. So that what this means is that when the length is more, the timing was more. When the length was reducing, so was the timing we had, it was faster, the timing was reducing. So that is looking more like the length of the thread as it reduces, so does the meter row swings, a lot more faster with a lot more frequency. And you recall that frequency is inversely proportional to the period of oscillation. So you can see that when the length was reducing, the timing was reducing. In other words, why is the timing reducing? It means that the oscillation took place swiftly, like the frequency was very high. In that regard, the period is going to reduce. So at 80, when we perform the experiment at length of 80 centimeter, when the thread was 80 centimeter, when we perform the experiment, the timing on the stopwatch was 18 seconds. When it was 70, it was 17.40. When it was 60, it was 15.50. When it was 50 centimeter, it took 14 seconds for 10 complete oscillation. And when the length of the thread was 40 centimeter, it took 13.20 seconds for 10 complete oscillation. Also, not to forget that the period, that's the time it will take to complete one cycle, one to and fro movement, is the total time taken divided by number of oscillations. So if we divide this 18 into 10 complete oscillations, so 18 divided by 10, that's going to mean 1.8. 17.40 divided by 10, 1.74. 15.50 divided by 10, 1.55. 14 divided by 10, 1.4. 13.20 seconds divided by 10, 1.32 seconds. So from this, we can be told to evaluate t square. T square here means the square of the period. So the unit now becomes seconds square. And that's exactly what you have here. We can as well be told to evaluate the log of t. The log of the period is what you have here. We can be told as well to evaluate the log of the length of the thread. The log of the length of the thread, log L, is what we have here. Take note of the units, for the table. So, and that ends that. The next thing here, as you can see on your screen in that question, is we were told to plot a graph of log T on the vertical axis and log L on the horizontal axis. Talking about simple harmonic motion or periodic motion, there was a particular question like that, alternative to practical physics. We performed, we had a lecture like that. The link to that lecture is going to be in the description of this video. In that particular lecture, we were plotting, I think, t square. Yes, t square versus the length. That was what we did there. But in this case, we were told to plot a graph of log t on the vertical axis. So this will be on the vertical axis. And we were told to plot, as you can see in the question, log L on the horizontal axis. This is the horizontal axis, log L on the horizontal axis. So the question can come, in various forms, but what is important is get your table prepared and then get ready to plot your graph. Okay, so the next thing, having plotted the table, is to now focus on our graph. Remember the rule, your graph should at least cover about 70 to 75% of the graph. So in doing that, we have to look at the lowest value that we have for log t and the highest. Okay, the lowest is this, and then the highest is this. So you're looking at 0.1 to 0.25. So on my own graph here, I'm thinking if I make this my zero origin, from here to here is about 2 centimeters on your graph book, 2 centimeters. Okay, 1, 2, 3, 4. How about if I make this about 8 centimeters? If I make that to be 0.100, yes, 0.100. That's what I'm thinking. So that 1, 2, 3, 4. This will be 0.200. This will be 0.200. And I'm going to 0.255. So if judging by what you have on a paper graph, then you're still going to have, more columns. Of course, your graph book is still going to extend. So I think this is the best way you should take it. So when I look at this, This is more like saying that, okay, this is more like saying 2 centimeter, 4 centimeter to represent 0.050, 0.050. That is what I am seeing here. That's the pattern I'm seeing. So looking at it that way, I can then decide to, if I've picked that, I can then decide to draw my vertical line. It must not be broken. That's why you must have a sharpened pencil. This time around, I am using a marker, of course, because this is a graph board. Okay, here we go. This is what we have. I've been able to draw that, and this here is going to represent my log t. This here is going to represent my log t in seconds. Log t in seconds. Then talking about my log L, the lowest here is 1.6 and the highest is 1.9. So what I'm thinking of doing is, if I say, 1, 2, 3, 4, 1, 1, 2, 3, 4, 2, yeah, that's just about it. So that I need to get my straight line for the horizontal axis. It must not be broken, and okay, that we've done for now. So this is going to be my log L in centimeters. This means 1, 2, 3, 4. I'm making this look like my 1.00. So it's 3 decimal places. 1.000. 1, 2, 3, 4. That's going to be like 2.000. So that I can then further break this down, this is going to mean 0.500, and this here is going to mean 1.500. So I'm going to have to put down my scale much later on, but okay, let me also get this completed. 0.051. So this is going to be 0.150, and that's just about it. So if you are using a paper graph, you can then continue this, till you get to 0.2, till you get to the next 2 centimeters is going to be 250. In 4 centimeter, the next 4 centimeter, like 1, 2, that's going to be 4 centimeter. From here to here is 4 centimeter. That will be 0.25, and then in about 8 centimeter, that's talking about 1, 2, 3, 4. That would have been 0.300, from which you can then pick your 0.255. So let's get into plotting the taking the point. So I'm going to start. Let me start from the lowest, 0.121, then 1.602. 0.121, if this is 0.1, 1, 2, 3, 4, 5, 6, 7, 8, that is going to be my, this is where I'm going to have my 0.121. Then 1.602, I'm going to have that 1, 2, 3, 4. This is going to be around here. So when I trace that up, okay, if I place my ruler this way, okay, that's looking here. Okay, so the next thing is to pick that point. So that's going to be somewhere around here. Okay, I've been able to pick that. And now the next one is 0.146. 0.146 and 1.699 around here. 0.146 is around here, and 1.699, this is 1.6. 1.6, that should be around here. So if I chase that up, that's around here. Okay, that's how it works there. That's how it works there. So that's 0.146 and 1.699. Then the next one is 0.19. 0.19. So we are looking at okay. So the next one is 0.19. 0.19 is going to be somewhere around here. 1.778 should be okay at the 11th, should be the 11th. That should be, yeah, somewhere here. We've been able to get that out. Okay, for now it's still looking like it. When you are plotting yours, you just continue this, and this is what you're going to have for that. So you look at if you look at the three we've had so far, you can see it all meets up. If you look at the three we've had thus far, it all meets up. So let me make that a bit more clearer. So you continue this pattern. Okay, you continue this pattern. If talking about a paper graph, you would have been able to get this up until, if you can have another 8 centimeter, you would have got this up to 3. And I can tell you that all of the points will be on this straight line without much stress. Okay, moving on. As you can see in the question, we were told to determine the slope S and the intercept C on the vertical axis. In this particular question, I, for one, do not think we have any intercept on the vertical axis. No, we don't have any intercept on the vertical axis here based on this question. But the slope is something that is very possible. How do we get out our slope? Okay, so how do we get out our slope? Okay, this is something we can do. We only need to just, get our triangle to get the best fit. Okay, I've been able to do that, and then I'm going to go get the horizontal part of the slope, talking about the x-axis. So if I draw my extrapolation, talking about my broken line, so that I get what the figure is on that particular axis, and then for this is what I am getting here. And then, okay, for the vertical axis, this is what I am getting. And then this. So you take note of all of those points. You see here, so that what I have here is my change in log t. in seconds, and what I have here is my change in log L in centimeter. So you see this and this and then this and this. So that ends that I'll be able to use this figure to get my slope. This figure here, this is 1.50 or 0.150. This is going to be 0.175. And this here is going to be 0.025. These are figures I'm going to use for my slope. Talking about my x-axis, this is 1.5. This is going to be 1.75 for my S2. And this here is going to be, this is 1.25. This here is going to be 1.400. So these are figures I'm going to use in getting my slope. Don't forget, if talking about my scale here, I should be saying log T in seconds. What I've used here is I've used 4 centimeter to represent 0.05 units. And for the vertical axis, that's the unit here should be, instead of writing unit, you can write seconds. And for log L in centimeter, my scale is 4 centimeter to represent 4 centimeter to represent 0.25 centimeters. That is what my scale is exactly like. So in your paper graph, you should be able to get another 8 centimeters. So from the 0.2, you're going to have another 8 centimeter, 2 centimeter, 2 centimeter, 2 centimeter, and like that. You get 8 centimeter, and that will represent 0.3. With that, you'll be able to pick this point and this point. I have been able to pick this point, and this point, and those 3 points, they just give me a straight line graph. So the next thing to do now is to calculate the slope and, of course, answer questions that follows. We're told to look for the slope of this graph. That's instruction 10. The slope here, the slope for this graph is going to be the normal. When we look for slope, it is the change in the vertical axis. The change in the vertical axis here talk about change in log T in seconds divided by change in log L in centimeter. Now, talking about change in log T, this is 0.175 minus 0.025, 0.025, all divided, this is going to be in seconds, all divided by that of L. In the case of L, we have 1.75 minus 1.40, all in centimeters. So going by this, 1.50, we're going to be having 0.15 seconds divided by 0.35 in centimeters. So this is going to give us, when we compute this from a calculator, this is going to give us 0.43 seconds per centimeters. 0.43 seconds per centimeters. We've been able to determine the slope, but talking about the horizontal, the intercept on the vertical, we don't have any intercept on the vertical axis here, but if we are talking about intercepts, C on the horizontal axis, the intercept C on the horizontal axis here talks about where, the graph touches on the horizontal axis. And looking at this, this is that is 1.575 centimeters. That is exactly what we have on the graph. That is where we have the intercept C. So the next question, we were told to state two precautions taken to ensure accurate results. As you can see on your screen, there are about 4 or 5 precautions. You write that as avoided zero error in deciding in reading the stopwatch. Yes, you avoided and corrected zero error on the stopwatch. You avoid error due to parallax in taking your reading on the meter rule and also on the stopwatch. You also ensure that the support, the two rotor stand, you ensure that the support is rigid, is balanced, and also you ensure that you displace the angle of oscillation is through a small angle, not through a very large angle. And that's just about that. Then looking at the next question, we were told to define simple harmonic motion. We were told to define simple harmonic motion. Oh well, simple harmonic motion, as you can see, is the motion of a body whose acceleration is always directed towards a fixed point and is proportional to the displacement from that point. So to the next question, looking at question B2, we're told to determine the value of L when T, the time of oscillation is 12 seconds. You recall that in this experiment, the number of oscillation is actually 10. So from this particular T, we can actually get our period. Our period there is going to be 12 seconds divided by 10, so that our period here is going to be 1.2 seconds. Now that we have the period as 1.2 seconds, we can look for the log of t. So log t here means log 1.2, and when you compute log 1.2, you're going to get 0.079 seconds. So it is this 0.079 seconds that we have to trace out from our graph. We need to trace out 0.079 seconds from our graph. When we trace out 0.079, we trace that, to the line of the graph, and we will see, we'll try to get where it touches on the horizontal axis. That we would have gotten log L, and from log L we can then reverse that back to L using our anti-logarithm. So 0.079, let's look at the graph. Log t equals to 0.079. 0.079 on this graph is exactly around here. This is exactly where 0.079 is. So that is exactly what we need to then trace, to cut the straight line, and we use that to determine the what our L is going to be. But first we have to get our log t first. So when we draw our extrapolated line, okay, this is exactly where it cuts on the graph. This is 0.079. 0.079. This is where it touches on the graph. So I'm going to trace that down, so that way I can get what exactly my log L is going to be. My log L here is going to be, when we trace that, this is what we got. This is exactly what we got. So this is 1.50, just a single hole after 1.50. So that is going to be 1.525. So what this means here is that is 1.525. If we trace this downward, this is 1.525. That is what that is going to give us. So that's what our log L is going to be, 1.525. Therefore, log L is going to be 1.525. Of course, what this will mean is that my L now is going to be, I could take anti-logarithm, anti-log 1.525. Okay, you can as well write that as anti-log 1.525. You press that on your calculator. So what we got when we compute this is 33.5. That is what our length is, 33.5 centimeters. So what that means is that when t is 12 seconds, we are going to be getting a period of 0.079 seconds, and that is going to be 33.5 centimeter for our L. That is what the question states that we should find. You look at it very well at from the table. When our when our T was 13.20, our L was 40. So if the timing had reduced to 12, so the length should also reduce correspondingly, and that is why the length is 33.5 centimeter, and that's just about answers that question. And with that, we've come to the end of this edition, talking about alternative B for Waec Practical 2024. For myself and the entire team, it's bye for now.